Hi there, and welcome to today's lesson in British Columbia Institute of Technology, Technology Teacher Education 4044, our material science structures class where we do a bunch of cool tech ed projects along with talking about structures. But right now in February, we are talking about structures and ways that we can analyze them. And we've been through and we've taken a look at classic truss analysis, and now we have a truss design challenge. And today I want to show you a few more advanced tools that you can do to get some really fancy design analysis and virtually test your trusses at home. And so if you're not familiar with the project, I've got a little bit of video right here. This should give you an idea of what it's going to look like. So these are two sections of the truss designed and AutoCAD cut on the laser cutter that we've got. And they have to support a weight. And they have to support that weight for 30 seconds. And there's some weight going on there. And it's holding that weight. And we want light trusses. And there we go. That's a very nice truss design. And so that's what we're trying to design and analyze in right here. So a couple of pieces of laser cut medium density fiberboard, or as we'll say, mention hardboard. Oh, just realized that this would be a lot easier for you to see if I move my picture down over here. Sorry about that. Okay, so there it is. It's all hanging off the end right there. And we're designing this truss. Today we're going to talk about how we can actually design these tensile members using string. So it's a genuine tensile member. But this is the general structure of the truss that we're designing. This one was from a couple of years ago, and their challenge had slightly different parameters. Anyway, let's come in here and let's get rid of that. So we're going to talk about how to do a linear static stress analysis and a structural buckling analysis, and a little bit about the material properties of hardboard versus medium density fiberboard, because we're going to use Fusion 360 and their default material only has medium density fiberboard, which is not quite the right material for what we're using. And it does make a difference to your analysis, both in terms of the mass of the structure, which matters for our challenge, and its stiffness. Okay, so let's get that out of there. And I'm just going to shrink myself down here and sit around in the bottom corner of this window right here. Before I get too far into it, I wanted to point out a really cool device that I happen to have here. And when we get into Fusion 360 and I start spinning things around, I have a 3D connection, 3D mouse that I'll be using just to come in there. And with that, I'll be able to rotate and pivot the views around. So if you don't see me using the little icon up at the top to do that rotation, you can use the icon up at the top right in here to do that rotation at home, but you won't need to in AutoCAD. Anyway, so I'm writing this tutorial assuming that you've had a class in AutoCAD or some familiarity with 2D drafting, and that you've been able to design your truss as a two-dimensional structure and get it all grouped together. And of course, oh, there we go. There we go. And when you put your mouse over top of the structure, it should be grouped. It should all come together, and it should be one contiguous structure. You should have little holes set up right in here for your dowels or for your bamboo skewers that we use to separate the two trusses to go through, and maybe a hole down at the back because we are going to be able to connect tensile members, and two big holes right here for your support members to go through. So we're going to take a look at how we can analyze this structure. Alrighty, now one of the things that we can do for analysis before we even go over to Fusion 360 is we can figure out how much this is going to weigh. And the way you can do that is by just typing in the hatch command. Okay. And then as you move your mouse around, you'll see that it's busy processing and it wants you to pick an internal point. And when you get the internal point just right, I don't know why it's giving me grief. If I click right here, there we go. I did have the point just right. You can see that the entire hatch fills the inside. And that's a good check to do to make sure that you've got the entire surface sealed on there and that you've done all your AutoCAD drawing correctly. Because if you don't have the surface sealed and you can't hatch it, then you're not going to be able to do all the fancy things that we're going to do in Inventor. And now if we come in here and we escape the hatch command, we can come and select our hatch and click on there, and we want to find the properties. Oh, I don't do this often enough on here to click on that hatch. There we go. If I click on that hatch and come over here to properties, had this all set up. There we go. So all you have to do is come in here and at your command, type in properties. Okay, that brings up the big properties window. And then when you come along here, get that hatch highlighted, click on it, and it will give you the area right down here for one cross section of your hatch. And of course, if you've got the cross section, you know that you're cutting it from 3mm thick material. So this is going to be the dimension in square millimeters. So you've got 17,000 square millimeters. Multiply that by 3mm. That gets you the volume of that cross section. Okay, multiply that by 2 because you've got the 2 cross sections. And then go ahead and just multiply that by the density of the hardboard that we're going to be using, which is somewhere around 0.9, which we'll get to in just a moment. You can actually determine that by taking a few very simple measurements in class. I'll leave that up to you to get a perfect value for the density so you can make a perfect mass estimation. But there you go. Just do a hatch and then the properties command, select the hatch. That gives you the cross-sectional area in square millimeters, multiplied by the thickness. Remember that you do have to convert from from cubic millimeters into cubic centimeters, and that is not simply a matter of converting by a factor of 10. You have to think about what a square millimeter and what a square centimeter is. Alrighty, so we can get at this. I'm just going to Control Z right out of here, get rid of my hatch, and get rid of the hatch. We don't want to export the hatch, but you can do some of your analysis and you can calculate your mass directly from your AutoCAD drawing. Now what you're going to do is you're going to take your AutoCAD drawing and you're going to save as, and you're going to save that file as a DXF file. So when the save as file comes up on here, I am just going to come in here and tell it that I want to save that as, oh, it doesn't have a save as DXF. Yes, it does, right down there. Find your DXF options right down at the bottom, and it really doesn't matter which one you use. Let's go with 2018. It's the latest DXF version, and just go ahead and save that as a DXF. Remember where you save it. And of course, I've done this before. I practice up. Now, you'll notice that in here I've got some spacers for holding the truss sections apart when I come down to glue them together that I'm going to laser cut. And I've got both sides of the truss on here, and I've got a boundary to make sure that I'm building this all within our legal 600 by 450 millimeter box. Don't worry about any of that. That will get imported to Fusion 360, but we'll just ignore it when it comes time to do our analysis. Okay, so basically complete your drawing in AutoCAD and get ready to export it to a DXF file. Remember to save it as well. Okay, I'll close that off right there. And the next thing that you're going to do is you're going to open up Fusion 360. Okay, now if you're brand new to using Fusion 360, it is an amazing program that lets you do all sorts of really cool stuff, including CNC machining and all of these calculations. But just a few things to look at. Over on this side, you've got cloud storage for all your projects. So you'll probably start out home here and create yourself a new project. Okay, now I've already got a project called Truss Analysis running, but why not create a new project and call it Truss Analysis and then go right into there. Okay, and as you can see, I've analyzed a lot of trusses over the last little while and used some of the cool generative design features in here to come up with some ideas. And yeah, it's anyway, I quite like this software, and I'm going to use it to show you how you can do this too, because It's amazing what you can do with it. Okay, so the first thing that we're going to have to do is that we are going to have to get a cross section into here. And so what we're going to do is we're going to create a sketch. Fusion 360 works by taking series of stretches and then extruding them into a third dimension. So let's start by clicking on the Create Sketch button. And then I'm just going to come over here, and you can see I've got 3 different planes laid out. And honestly, it doesn't matter which one you choose, but probably easiest if I choose the front. Now, as far as rotating and moving things around in there, I have my fancy 3D mouse, so I can just pivot around like that. But you've got this little, I forget what they call it up here, this little icon. The view cube, I think, is the name of it. And if you click on parts of it, that can bring you to the front as well. Okay, so if you see things start to slip around in that and you don't see how I'm doing it, that's my fancy mouse. You can come up here and do the same thing by picking that up and pivoting. You can zoom in and out with the scroll button on your mouse, and you've got a few more view options down here to control how you orbit about things, look at things, and I'll let you play around with those because that's not what this video is all about. Okay, so I clicked on one of those 3 planes, and now you can see I'm looking at the front, and my icons up at the top have all changed along here because I am in sketch mode. You'll see sketch mode highlighted in blue right there. Okay, and now what I need to do is I need to insert that DXF that I just saved, okay? You can insert other formats too. SVG is quite common for some graphic stuff. MasterCard components, that's more for 3D, but we're gonna go insert, and we're gonna insert a DXF. And now what you have to do is you have to select that DXF file, and it will look on your hard drive, and I want to go over to OneDrive. BCIT. Remember, I said you have to remember where you save it. Oh my goodness, I've got way too many folders in here. Um, there we go. That's where I saved it, right to that root folder so that I knew I could find it again. And let's bring that in. And what's going to happen is that file is now going to come in. That's going to get uploaded to the cloud. It's going to ask you, what did you draw it in? Well, of course, you drew it in millimeters because inches are really a stupid unit of measurement. And there we go. We'll just click OK. And now if this came in okay, as you move your mouse around, you should see that Fusion 360 is able to pick up on various enclosed boundaries in here. And there's my truss standing out as an enclosed boundary. That's great. That means that we're going to be able to extrude that out. Later on, I'll do a different video and I'll show you how you can draw this truss entirely within Fusion 360, which lets you use the parametric modeling capabilities of Fusion 360 to come back and easily edit the truss within Fusion. But for right now, you've got a truss in AutoCAD, and this is how you analyze it. So I'm just going to click on Finish Sketch right here. Okay, now I've got this. I've gone back to my 3D view. Okay, I clicked on the Finish Sketch. I'm back in my 3D view. I can pivot around in here with my view cube. I can look at it from different sides. And remember, I said we're going to ignore some of this other stuff. We're just going to take a look at this one cross section right here. And we're going to take that cross section, and I'm going to hit the Extrude button right up here at the top. Now, if you mouse over your commands on here, Fusion 360 is pretty good. It's going to drop a little box to explain what you're about to do, and it will pop up a box over here when you click on it. And this box has a number of different options on how you're going to extrude it. We are going to select a profile. So we're going to select this profile right here. Notice how the truss went dark. None of the holes went dark because they're not part of the profile. I click on it right there. Then it says, how far do I want to extrude it? I am going to extrude that 3 millimeters, and I am going to have that become a new body. All right. Now, there is a 3-dimensional representation of one section of your truss. How hard is that? Okay, we're into 3D, and so we imported a sketch, we finished the sketch, we did an extrude, and now we're in here, and we've got this section right along here, and what I want to do is I want to do the move and copy command because we need two sections of this for us to analyze. It says, what do I want to move? I want to move a body. This is still a body. We'll turn it into a component later on. And just zoom in right here now. It's important that when you grip it, that you're not gripping on some weird face that, is off at an angle. Like, actually, most of these are pretty good. So just come along here and grip it about like so. So I've got an arrow pointing out perfectly perpendicular to that. Okay, and now you can just drag that. Oh, I did it wrong. I have to click Create Copy. Remember to click that Create Copy button. I always forget that bit. Okay, and now when I move it along, I can come along here. Now this is where I set the width of my truss. And the minimum gap that we're allowed is 40 millimeters in between the truss. So in order to get that gap, remember that the truss is 3 millimeters thick. I have to move it 43 millimeters apart. Okay, so there we go. Now I've used the Z distance and that works because of the way I clicked on it, but that's why I say drag it out a little bit and it will prompt you to let you know which you should be using. If you use one of the other ones, it's going to end up with the two sides just higher than each other. You want them separated from each other. And I'm going to click OK right on here. And now you've got the two sections of your truss right next to each other. And darn, they're looking good. Okay, now over here, you've got the hierarchy of what's going on, and we've got these tucked away in the body. Okay, and we can change the name of this to Truss Section 1. And you can change this to, oh, make sure you click on what you want first. Escape is really handy, always gets you out of there. Control Z I always find is handy too, but we should be able to come in there and on body 2, I should be able to just rename that. Okay, something weird just went on there. If you ever end up in here, just click Finish Sketch and we're done. Control Z to get rid of all that. There we go. Redo is great if you go back too far. And now I can come on there. I'd whacked a key one too soon. Truss, section 2. Okay, so I've got two truss sections there. Now I want to apply a material to them. And so all I need to do is come in here and right click on one of them. And so that was a right click, not just a regular click. Use the right mouse button. And we're going to pick the physical material to assign right on there. And this window will pop up right over here. And it'll give you some choices. So if you're making this all out of steel, you could analyze it in steel, but we're going to go down to wood. And it's going to give us a selection of woods. Now, not every one of the woods is going to work for the analysis that we want to do because many of the woods are anisotropic material. All one word, anisotropic, means that they have different material properties in different directions. And we know this, wood splits easily in one direction, not the other. It's one of the reasons that we use medium density fiberboard instead of a thin sheet of balsa or something like this for structure, because medium density fiberboard, or in our case, hardboard, is a great material. We'll just bring that right up here and we'll drop it into here so that we can use it in this design. Now, I've got a document in here, and you'll find this if you're in the course. It's available on our Desire to Learn page. And if you're not in the course, well, here's the document. It's about 2 pages where when I started this project, I came along and said, I think it's time to research some of the differences in materials that we're taking a look at. And there are some big differences between a generic MDF material that's being used in AutoCAD, right, or in Fusion right here, and the actual stuff that you might buy on the shelf. And it's interesting because different manufacturers are going to have slightly different material properties for their material. And so I've come along with some estimates that you might get for the material properties. What we're mainly concerned about in here is the density, which controls how much it weighs, and the modulus of elasticity, which controls how stretchy it is and when it's going to buckle. So those two are going to be critical values. But if you read on here, there's more description of what's going on in there. And there you go. I think if you pause the video right there, you can probably read that if you're watching the high def version. Anyway, 0.95 grams per cubic centimeter is a rough estimate of the density. It's not the perfect estimate. So those of you in my class who want a more perfect simulation will have to figure out how to figure out the density of the material that we're dealing with. And that is a rough estimation of the modulus of elasticity of standard hardboard, but it's probably not perfect. And the material that we're using may have come from a different manufacturer, and you'll have to use some of our beam bending formulas and structural buckling formulas that we've talked about in class to get maybe a better estimate of the modulus of elasticity of this material, because as you can see, there is a fair bit of variation in what you might see from hardboard, anywhere from modulus of 3.2 all the way up to 4.6. When I said 3.7 in there, I just took a midpoint. That material I'm giving you may or may not be 3.7 gigapascals for a modulus of elasticity, and it will affect your simulation. Garbage in, garbage out, you give your simulation a bad value, you get a bad answer. However, we're going to carry on with these values. They're close enough to make a first estimate. Okay, so what we have to do to get those values in here is we have to come in here and right click on that material, and we're going to edit that up. Actually, I have to bring that window over or else it shows up on my other window. And then you have to click on Advanced. And in Advanced, you have to go to the physical properties of that material, and you have to go to the mechanical properties. And so there's the Young's modulus, and we're going to edit that. So MDF was estimating would have a modulus of 2.4 gigapascals. Our hardboard is probably closer to 3.7. And the density it was saying was closer to 0.8, which seems a bit low. I'm going to use 0.95, and I'm going to apply that. And then I'm going to say, go over here to the appearance. Now, just because I've edited that, I don't want it to have the exact same color. Now, you can pick a wild and wacky color for your MDF. You can make your MDF any color you want. I'm just going to change it a little bit from what it is. Try and, where's a nice brown in there? There we go. Doesn't really matter. I just want, that's not brown, it's green. Okay, we've got green MDF. Click apply. Okay, I'm done. Cancel my changes. And now I can take that material and I can drag it onto truss section 1, and you'll see that the color changed slightly. Then I can drag it onto truss section 2 and the color changed slightly. So now those two truss sections have been updated with the correct materials so that Fusion 360 actually knows what they're made out of. Okay, now we need to add some little connections going across from one side to the other. So to do that, we have to create another sketch, and we have to extrude that sketch. So we come up here to our Create Sketch button again, and now we come in here and we want to pick an outside surface. See how that outside surface highlighted when I picked it? Okay, click on it. Now, if that disappears all off your screen, don't panic. Just come down here. There's a little magnifying glass right there and tell it you want to fit everything back onto the screen, and you'll be good. Okay, now we've projected this on here, and so now we've got the two sections lined up right on here like this, and we want to be able to extrude a profile across all of those little holes. So to do that, we're going to do a project command. Now you can use the create in here to find project, or you can just hit the letter P on your keyboard. P brings up this profile, and I am just going to click, and see how everything went red right there around the outline? That means that is a profile that I am going to project into my current sketch plane. Then I can click OK. And that's all you have to do to create the sketch. We just needed to go out there and find the things that were already existing and say, okay, just project them onto this sketch plane. And I know it doesn't look any different aside from these little dots here, but those dots are useful. I'm just going to click Finish Sketch now. And we now have a new sketch that exists right here. Now, everything we do has a timeline and a history on it, so we can actually go back and we can edit things and we can drag this back and forth, and that'll be really important as you get into modeling more complex structures. We can also see our sketches showing up in the hierarchy, and our first sketch right there, you can see when I mouse over it, is still visible, but it's just visibility has been turned off. Our new sketch is right in here, and this is what's going to allow us to create our cross sections. There's one more thing I have to do. Remember how I said this was a timeline right on here? If you want to go back and edit something, you can just come in here, select it, and then double click on it. And that takes you right back into sketch mode. I have one more thing I have to do. Right down here. So this is going to be my load node. And if I zoom in very closely on the load node, I want to take a line right here. And it doesn't matter exactly where I get it. I just have to put a flat bottom on there. So draw a little line right across there like that. Okay. And then click a check mark. Now I can finish the sketch. That flat bottom is going to be useful later on because that's going to provide a reference direction for the load to be applied. It's not exactly perfect according to our models, but it's going to make the rest of our analysis go a lot easier. Okay, and now we need to do another extrude command. So I come up here and I hit my extrude, and this is going to take a minute here because we have to come along and we very carefully have to select the inside of each of those nodes. Now, if you happen to accidentally click on the outside and see that highlight and go blue, we don't want to extrude all that. We've already done that. So just click it again and that will clear. So we want little blue nodes. And we're just doing the little ones right now because those are the ones that are going to get glued into our structure. I'm moving this around by pressing and holding on the center mouse button and zooming by rotating the center mouse button. Now, you may have more like this or fewer like this. But this is what it takes me to go through, and you'll see that I'm working my way out, making sure I don't miss any of them. Then I come out to this node right here, and I make sure that I just click the circle, and I leave that tiny little bottom part beneath the line unselected. Okay, that stays gray. So now we've got that all selected. Just rotating it so you can see it a little bit easier what I'm about to do. And now I'm in the middle of extrude right here. I've selected the profiles that I want to extrude out. And I could do a distance extrude, but it's often easier in this case to tell it I want to go to an object and then rotate this around. I was looking at the front. Let's go take a look at the back over here. So they're going to start on that side, and you can see them highlighted out on that face right there. And I want to extrude them all the way through to this face right there and join them together. And when I do that and I click OK, that joins them all together, and it also joins the two truss sections together. Now, to be perfectly honest, we're using bamboo skewers or dowels in here. They're going to have slightly different density and slightly different material properties. And we can model that, but it makes our simulation a lot more complex, and it doesn't really improve the results all that much. So this is a nice little step that we can do right in here to get this all set up right here. And now you have your structure coming together right here. It should all be together as truss section 1. And if you come into truss section 1, right click on that and go to properties, you can come down here and it will tell you that this section has a mass of 106.17 grams. And I believe when I weighed this in the shop, it came out at 102 grams. So fairly close approximation. But remember, if your density's off a little bit, then your mass is going to be off a little bit too, because it only knows what you tell it. Okay, if you feed it bad data, it's going to give you a bad answer. We fed it pretty good data, it gave us a pretty good answer. If you want perfect data for mass, it can give you a perfect answer. Okay, so now our truss is put together like this. Now, I haven't added the string yet. Okay, I'm going to have some string coming around right here and going to bring it down right into here. I will show you how to add the string later on. I'm just going to go through and do a couple more things to get this set up in order to do an analysis. The first thing I'm going to do is I'm going to come in here and on my truss section, I'm going to right click and I'm going to say create components from bodies. See that one right there? Create components from bodies. What's the difference between a component and a body? You can make joints in between components, but you can't make joints in between bodies. It gets a lot deeper than that, and I'm sure the Fusion 360 people, if a Fusion 360 programmer was watching this, they'd tell me, no, 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 it's more complex than that. What we're going to do right now is we are going to make the steel supports that run through right here, and we are going to joint them in here so that we can hold that together. And you know what? To do that again, we're going to do another sketch and an extrude. So I'm going to create a sketch, choose this surface right here. Oops, can't see it all, so just click fit, and it brings it all back into place. And I'm going to do the rear one first. Now, this is going to be our one that's fixed in place. It's the simpler of the two to do. They're both pretty easy, but all I need to do is I just need to come in here and use that project command, okay, or hit the P key, and I just need to project that circle this time. So you can see it says one selected, and I say okay. And now I've got a circle right there. I finished that sketch. I'll sometimes change this a little bit so I can see my extrude as it happens. And I've finished the sketch. I'm going to extrude this profile plane. And over here, normally it just says direction one side. I'm going to extrude that two sides. One's going to come out here. The other one's going to come out right there. And rather than joining that, I am going to create a new component. And you'll see the color changes, and now that's actually made out of the default material, which happens to be steel. Doesn't really matter how long it comes out. That's not part of your weight for the truss because it's a different component. All that is that's the bar that you're going to be leaning down at the back to hold it in place. Okay, and I can just click OK right there. So now we've got one steel bar going through there, and we come back and we do the same thing again. Create a sketch, click on the surface, fit to get that right in there. Zoom in a little bit. P for project. The circle that we want to draw to, click OK. Finish that sketch. Maybe rotate it a little bit so that you can see what you're doing. And then extrude this profile. Doesn't matter what direction. Now that's only one direction. We want that to come out two sides. Remember to change that to two sides. Drag it through the other side. And oh, you know what I forgot to do? Cancel all that. I've got to go back to this sketch. It was the exact same thing that I forgot to do on the load node. Got to come in here, zoom in. Oh, to get back in here, I just double clicked on the sketch right there. So if you make a mistake, it's pretty easy to fix in here. You just go back on the timeline to find out where you made the mistake, and then you fix the mistake. I needed a little line like that because this is the restraint that's going to be resting on the table, and that's going to be what we call our frictionless constraint right in here, but we need to have a surface on it so we can indicate which direction it's fixed in. Now I can finish my sketch. I've got a little line right there. Now you can see that profile is the one that I'm going to want to extrude so that I get a flat bottom piece. It's not really flat bottomed in the real world, but again, it's close enough and makes our simulation go easier. So you finish the sketch, you extrude the flat bottom profile, and again, we're going to do two sides, and the distance doesn't really matter all that much. two sides, extent type, distance, and distance, and new component. We don't want it coming out the same color as our truss. Okay, and now you'll see component 2 right there, and when I mouse over it, notice how it highlights. We can come in here and change that name to rear support or roller support if you prefer, because that will be the roller support. And this is our, okay. Now, right now, Fusion 360 knows that we've got these components in here, but it doesn't quite know how they're joined. Are they glued together at that edge? Are they free to rotate? Well, for our truss to actually make sense, these need to be able to slide back and forth a little bit in here and rotate around there. And this is where we're going to assemble them. And so you come up to the assemble tag right here and tell it you want an as-built joint. An as-built joint just means that we've drawn this in the right place. We just need to provide a bit of information on how the two parts behave. Okay, so under as-built joint, it says select your components. Now before we get doing that, change your type of joint to a cylindrical joint. Then you can select this component right here and then zoom in. Okay, and components, one selected, motion, cylindrical, and then select right there. And then finally, it'll ask you to pick the snap side. We should be able to pick right there. And it should be a cylindrical joint. Snap right there. There we go. And now you can see it comes through there. You can preview the motion. This should give you how it can move. It can rotate around in there just like a pin joint. Okay. So that should be jointed in there and it should be moving around nicely. We click OK. And you'll see right down here on our timeline, we created a joint. Now, if there's a problem with that joint and you need to fix it up, you can come in there and click on that. And you can say, well, which components are selected? Those are the components that are selected. What's your snap face right there? How does it look when it moves? And then you can click OK again. So that's on your timeline. You'll see another joint show up in just a moment because we are going to assemble another as-built joint. Again, it's going to be cylindrical between our forward support and the truss, and it's going to need to know what the snap is right on there. There you go, you'll see it slide in and out. When you preview the motion, there it is sliding around a nice cylindrical joint right in there. Click OK. All right, now we haven't added the string yet, but I'll come back and show you the string in just a moment. It's quite possible that you're building a truss without any string, and so you don't need that. I'm going to take you over to the simulation mode, and we're going to be able to simulate this truss. Now, before we go there, it's always a good idea to save your files. And if you just click on the Save button, it's going to ask you, what do you want to name this? Okay, this is Truss Demo 2023. And where am I going to save that? I'm going to save it in my truss analysis folder, and I click save. Now this is being stored on the cloud. So if you want a copy of it on your flash drive or something, you'll have to do an export and take that. But this is being saved to the cloud using your Autodesk account to store it. And I've had really good luck. Autodesk has taken very good care of my files. So there we go. We've got a file name up here. It's all saved and ready to go. Now I'm going to come over here and I'm going to go into Fusion 360's simulation mode, which is really awesome. So over in the simulation mode right in here, it can do a whole bunch of simulation. Now, when I was an engineering student, finite element analysis and numerical simulation was definitely graduate level work. One of my fourth year classes did get into a numerical method for solving problems, but we were only doing a two-dimensional solving technique. And one of the reasons is that because when you do this solving technique, you can see on this image right here that the surface is all broken down into elements. That's what it means by finite element. You break this very complex surface down into a finite, countable, number of elements, little parts. And then you analyze how each little part interacts with each other little part. And through doing that, you're able to predict how the entire structure is going to change under load. 20 years ago, you had to figure out the meshing, the creation of this mesh, the creation of all the elements by yourself, and the interactions you had to go through and basically dot by dot by dot create the mathematical model of your structure. Fusion 360 has some very clever programmers who've solved that problem for you. The first test that we're going to do on it will be the static stress test. And then later on, we'll come back and we'll do a structural buckling test, which is a really complex test that most finite element packages that you can get for free. Thanks, AutoCAD. We like being educators and we like being students. It's one of the benefits. You can't get access to this anywhere, and Autodesk will solve the problem on the cloud for you. So long as your computer's powerful enough to run Fusion 360, which even has a web interface, meaning you could theoretically do this on an iPad, I think, you're going to have enough power to do this on your computer. There's other analysis that it can perform, and some of them are really cool. So you can do a thermal stress analysis, so you can watch heat flow through an element. You can do nonlinear static stress, so if you're working with a material that doesn't respond in a linear fashion. You can do event simulation, so if you're going to drop a ball onto an object or fire a bullet into a wall and you want to watch what that kinetic energy does, you can test that out. Right down there, dynamic event simulation, that's the one that does that. It's got some really cool things for shape optimization and generative design. We're not going to get into all that, but it's really cool what it can do. And in the event that you happen to be doing injection molding and you want to know how your plastic's going to flow through there, you can think about that as a really interesting challenge because, of course, the plastic's solidifying as you inject it into the mold, or at least it's cooling down as you inject it into the mold, yet you need it to stay liquid and molten until you can get it all the way through the mold. Interesting stuff. Anyway, static stress for us is how we're starting out. We're going to create a study. There we go. When you click that Create Study button, you can see that we're in the simulation mode. We have a whole new menu along up at the top. Now, thankfully, we've done a lot of work. We've put our materials in here, and really, this is how simple it is. You come to your constraints and tell it we've got a structural constraint. Remember when we do our truss analysis, you've got your roller constraint and your fixed constraint. Well, here's a fixed constraint, and what's going to be fixed is this rear node that somebody's holding on to. And that's all you need to do. You just need to say that is fixed. Now, if we're doing more complex things, we can turn off some of the positions that it's fixed in, but we just leave those all on. That steel beam's not going anywhere. Okay. Now our next constraint is also a structural constraint, but we're going to call this a frictionless constraint. And look at that. See the rollers on there? Sure looks like things we've been modeling with our trusses. Now I do have to rotate this around so I can see down and remember that flat side that I almost forgot to put in there. Well, it's really handy to have it right there because now I'm just going to say that is going to be our frictionless surface because that's going to be resting on a hard flat surface. I could have gone along and modeled a hard flat surface and put the joints in there, but this saves me a lot of modeling and effort, and the results come out pretty reliable. So there we go. That's fixed in right there. So in our standard truss analysis, we've got two constraints and we've got one load. So we come up to the loads and tell it we have a structural load. Then if we come down here, remember this is another line that I almost forgot. Now careful when you pick it. You don't want to just get one of the lines. You want to get the big flat surface. You can see the difference. There's a line and there's the face. Okay. Now you'll notice that those arrows are all pointing up, which means shoving that up. We actually want to change that direction. So hit flip direction and we are going to load that with 30 newtons of force. Okay. Or 3 kilograms. Now, those of you who are being really fussy might come along with your calculator and say, I'm going to be even more precise because I know that it's actually 9.8 newtons per kilogram at Earth's surface, but 30 newtons will do just fine for our modeling. you can be more precise if you want. And there we go. Now we've got one arrow pulling down right on there. And of course it expands to show that we've evenly distributed it across this surface. Yeah, it's close enough. We could have got fussier in our modeling and shown exactly where we were going to put that hook. But as far as the overall structure goes, having it spread across out there seems to work pretty well. Now, we have to do one more thing on here. We have to come in here and tell it that we want automatic contact generation. Now, this again was something that you would have had to do yourself back in the day. Click on automatic contacts. Okay, and just click generate. What it's doing right now is it's going through and it's looking to say, where does this and where does this meet with the structure? If we've done that all right, we can come to solve and we can go pre-check, and it should say study setup has all the information required. If it tells you something other than that, you might have to go back and redo your automatic contact generation, or you might have to check to make sure that your loads are in there. You can see your loads by looking right in here and expanding this menu, and you can see that I've got gravity turned off. I'd love to do that when I'm cycling up mountains in the summertime. That would kind of take the challenge away, but it would sure be handy sometimes. I've got a force in there, and here's my constraints. And if I put my mouse over top of them, I can see where those constraints are. You can see in here little markers popping up to highlight and show where those surfaces are. And if I need to edit them, I can come in here and click on the little pen button right there to go ahead and edit that all up. All right, it's ready to go. I'm going to hit the solve button, and I'm going to hit solve. And you can see this window pops up right here. If you were a paying customer of AutoCAD services, you would have to purchase cloud credits that would allow you to solve this. Given that you're an education student, Autodesk wants you to get used to using their software so that you and your future students go out and become paying customers of Autodesk, and use this to solve their engineering problems, for which they'll very happily pay cloud credits, because this is an amazing service that they provide. Okay, so let's click Solve One Study. And now your model is being uploaded to Autodesk's cloud servers, and it's going to run off and it's going to do an analysis. And that's all running in the background. It'll let us know when it's done. We can just click close. If you want to monitor the progress, you can take a look right up here at the notification center, and it will tell you what's going on right in there. Oh, look, it just said it started successfully 26 seconds ago. It'll go through, it'll generate that, it'll let us know while it's done. So what I'm going to do while I'm waiting is I'm going to right click on the static stress, and I'm going to go clone study. So I've got study 1 says static stress. Study 2 right in here, I'm going to come down to this and I'm going to right click on that, and I'm going to come into settings. And I am going to change it from static stress to structural buckling. Now, in here it asks me how many modes of failure do I want to calculate for structural buckling, and I am going to tell it 50 modes. You'll see why when we're done. It's a weird thing about structural buckling analysis, and something that I haven't 100% figured out, but give it 50 modes and you shouldn't have to worry too much about it. Just click OK. All right, we now have a structural buckling study set up, and because we cloned that first study that already had all the information that it needed, we should have our load case in here. Here's our loads. We've got a force right out here. We've got fixed and frictionless joints right in there. Our contacts have been generated. We should be able to go solve. Let's do our pre-check to make sure it's okay. It says it's okay. And let's go ahead and tell it to solve. And we've got one thing running already. Let's click Solve One Study. And now it's structuring that job. Last time I looked, you saw that would have cost me 6 cloud credits if I was a paying customer. I I think cloud credits were about $1 US. So uh, that would start to get expensive if you were running it along. Okay, look at that. Our static stress study has now completed on their servers. So while the structural buckling finishes off, I can come back in here and I can activate my static stress study by putting my mouse over top of that line and clicking on that little dot. Come on, activate. There we go. And it automatically takes me to my results. And this lets me see a nice shiny little picture of what's going on. Now, generally, you don't want your safety factor to be less than 1. Okay, and in fact, it's got a little article on here of safety factor targets, and you can study safety factors for things like bridges and that are crucial for human health and life and safety. Safety factors are like 10, 20, 30 times. They're pretty high. But for our truss, we'd like our safety factor to be up to 1. That means that the strength of the material is 100% strong enough to hold the applied load. However, if we take a look at this, you can see that the section that tells you that it's going to be at only 33% of the applied load is just this little section right out here where we applied a hardboard material, and really we know that's going to be a bamboo truss or a piece of dowel running across right there. It was one of the weak parts of our modeling, but it's probably not too bad. It is applying that stress into the rest of the structure, and we can see a deformed shape right here. Now this deformation is exaggerated a little bit. You see I've got a deformation scale right down here in this dialog box, and if I go to the actual deformation in here, we're looking at a couple of millimeters of deformation, but to really make it stand out, it gives you an adjusted deformation so that you can see where the deformation is going to be happening. So keep in mind, this is a magnified deformation taking place right here. Okay, and now let me just move this out of the way right here. I'm just going to close this window. And now you can see on here what the different colors mean. So red means it's probably going to not be strong enough there. So if I come back right in here, you can see that some members, some parts of the member right in here are nearing a point where they're just about ready to fail. Thankfully, the rest of the member is still going to be strong enough to support that. So there's definitely a tensile load concentration right in here and a compressive load concentration right in here as that load comes back through there, but it doesn't go all the way across the beam. I think we've got a good chance of this holding because this material on the top side has a safety factor of like 8 plus. And you can see that all of our little cross members, aside from that one that took the load, are really strong. And up here where I don't have any wires or ropes or anything, there's no load happening up there at all. So there's no stress and massive safety factors right up there. We'll see if we can change that up in a little bit. Now, this analysis is really critical to do before you do the structural buckling, because if something fails in static stress, if you see red all the way across a member in here, then it's going to fail right there. And in fact, even if you see red 50% of the way across a member, you might have something to worry about. Okay, so just keep that in mind. This one looks like it could do with maybe a little bit reinforcement back here. We know from testing that that's going to hold, but it's a close thing. In fact, we found that that structure actually broke somewhere, when I tested this, somewhere between 3 and 3.5 kilos. All right, our structural buckling is finished. So this is static stress. This is how things are going to break as they're being pushed and pulled, but it doesn't account for the fact that when you load something in compression, it buckles out to the side. So let's come down here and take a look in here. And since our static stress is good, we should be able to come in here and take a look. And oh, look at this, our buckling mode number 1. We didn't need all 50 of them. Our buckling mode number 1 is at 1.3 times our load. So this is predicting this is going to be able to handle, close to 4 kilos. Like I say, ours broke at When I tested this for real, it broke at somewhere between 3 and 3.5 kilos. So maybe my elastic modulus is a little bit high in this model. I entered a value of 3.7. That might be just a bit high. Now, looking at that right there, you can see what's happened is that this is pulled down and the bottom members go into compression. They don't fail in compression. They fail by buckling, okay? And you can see that pops out to the side. And as soon as that starts to pop out to the side, your geometry's changed. And if you were to go back and do a static stress on this one, you'd see huge amounts of static stress in here because it's now got the buckled deformation in there and it's going to fail. What you're looking at on here is actually how much it's buckled. That's not necessarily um, well, it's a pretty good idea of where the worst buckling is going to occur. Now, there's different ways that things can buckle, and you have to be able to analyze what's going on a little bit because some of them don't make sense. Like that first one makes sense, and this one kind of makes sense that, it's going to buckle in compression in the bottom. But you'll notice some of them have negative factors in the beginning, and there's no way that it's going to buckle like that, okay? Because the top is going to be in tension. How the heck is the top going to buckle? What the negatives indicate is if you reverse the load, how's it going to behave? They're not really relevant to what we want to solve, but somehow the structural buckling engine always feels obliged to report them just so that you know that they're there. I haven't figured out that aspect of structural buckling, but it's there. So what have we got from this analysis? Well, we've got a truss. We checked its weight. It's going to be about 106 grams. And we've tested its strength in static stress, where it looks like it's probably going to hold. And we've tested in structural buckling, where it looks like it's going to break at 1.33 times the load. The load that we applied was 30 newtons, so that's going to break somewhere around 40 newtons, it predicts. I think the value that I put in for Young's modulus, 3.7 gigapascals, was a bit high. But if you want a more accurate value, you're going to have to go and spend some time in the shop and do a couple little beam bending calculations to try and get a more accurate value. All I know, 3.7 might be a bit high. No, I'm not going to tell you what my calculations were, but I will show you how to do them. Okay, so let's take a look right in here, and that's good. Now, if you've just got a basic structure with no cables, you can stop right there. If you've got some cables on it, I'm going to show you how to add the cables in there. I'm going to finish my results. Okay, and now I'm going to come back to my design. Now, in my design, I could come in here and make a few different tweaks. Here's how I am going to add the cables. I'm going to do a little bit of a shortcut. And again, a little bit of a simplification, but a simplification that I've tested that doesn't seem to affect our results so much. And we're going to need a new structure. I'm going to assume that you've got a cable on this side running just down the inside and a cable on this side running just down inside here. Okay, now in order to put those on there, I need to get a new construction plane to draw the cable onto. Okay, you'll remember that up until now we've been drawing planes either on the X, Y, or Z plane, or we've been drawing them on the surface of a material. I need to create an offset plane. So I click Offset Plane under Construct. And I come in here and it asks me, well, what surface do I want to start from? And I'm going to click the inside plane right here. Okay, and it says, how much do I want to offset it by? I am going to offset it 1 millimeter. So if I look at that from the top now, instead of having this, let me just click on the top right here so I look perfectly down. You can, there we go. You can see that there's that thin orange line. That's going to be my new plane, just inserted a little bit. I might make it 1.5 millimeters. Just thinking about where I've been able to tie my string, it's closer to 1.5 in there. And I'm just going to click OK. All right, bring that around. And now that plane is all lit up right there. And that's where I'm going to create my drawing. So now I'm going to create a sketch. It's going to say, what plane do I want? I can click on my new plane right there. And I'm going to go ahead and I'm going to draw that in there. Now, the truss is going to get in my way a little bit here. So what I'm going to do is I'm going to project the section onto that onto the plane, and then I'm going to temporarily turn the truss off so I'm not looking at it. So just come along and go P for project. Click on, well, actually you don't have to project the whole thing. Let's project the points where we're going to put it. Now I know we've got this little hole right here. We're not going to use that one. We're going to use the big steel rod down here at the back, just because it's a little easier to model. You're not allowed to tie your rope around there because that would be a big fuss for loading and unloading. You're going to tie it right here. It's not going to make a huge difference overall. Then my rope is going to come up and it's going to go around. Oh, sorry, I'm going to project that one. I'm going to click OK. Then I'm going to hit P for project. And it's not letting me select right there. I want to get that dowel in right there. So you can come over here and just tell it, I want that dowel project on there. Do you see that little red ring? Then it's going to come down right to here. I'm going to click right there, and I'm going to say, okay, I'm going to project those two onto that surface. And now I'm just going to come in here and I am going to find my truss, and I'm going to turn it off. There we go. Now I've got my two supports and two little circles representing the nodes that I'm going to connect to. Look at that from the front again, and here we go. Okay, now I'm going to go create a circle. So I click on the circle down here, and I'm going to tie my structure right about this one right here. So I'm just going to draw a circle. And I know that my outside of that circle is 13 millimeters. I'm going to say 14 millimeters. I'm going to assume that I've got a 1 millimeter square cross section of material. It's not a perfect analysis, but it sure simplifies things. I'm going to come up here, and now I could do the circle thing again. It also has an offset command. It works just like AutoCAD's offset. So I can come in here. I can have that come out 1 millimeter. And I'm going to come down here, and I'm going to offset that 1 millimeter. Okay, those are my knots. So I've modeled the knots in there. They're grabbing tight onto those three beams that I've mentioned. Now I need to add the string, and I'm going to add a line. And if I click right here, this lets me make a construction line, so it'll show up dotted. And I'm going to come from the center right here. So I want my construction line to come from the center right there. Make sure you've got the center. Okay, and come up here to the center right there. Where's my other? There's my other little. Then I'm just going to click the little check mark to let it know that I'm done drawing lines. And now I've got, no, you can hit the escape key if it still keeps enthusiastically trying to help you with lines. So that's where I'm going to run my string. Now, this is going to be a little bit inaccurate, but it's still good enough, I think, to work. Because obviously these are perfectly straight lines, which means that you've got that string tension so that it sits in a perfectly straight line. I think a very slight, like a 1 millimeter arc right in here and a 1 millimeter arc right in there would probably simulate your slightly loose lines that you put in there a little bit better. But I've done some testing and this isn't too bad, so I'm going to stick with that. Now, a straight line, we can't extrude this because it's just a line. We need to take this, we need to turn off our construction line mode. We're going to modify that. We're going to offset, and we're going to take that structure and we're going to offset it 0.5 millimeters. Okay, and now you can see we've got a solid line right there. And now we're going to go modify offset, or just hit the O button, and we're going to move that minus 0.5 millimeters. Okay, so that extrudes it on two different sides right there. Now you can see that we're going to have a closed surface that we're going to be able to extrude from. Okay, I'm going to finish that sketch because I'm ready to do some extrusion. And now I'm going to do that extrude command. We should be getting pretty familiar with extrude. And I'm going to come in and I'm very carefully going to select this surface right here, this surface right here. Okay, make sure that it goes all the way around. Right there, that's my string. It's going to come up right to here. It's in a knot right around here. Make sure the knot goes all the way around. Pick the line coming up there. Now I'm not picking any of that because that's in the middle of existing material. Then I'm going to come right down in here and finish that off. Okay, and that is going to extrude a distance. Depends what cross-sectional area of string you want. So you kind of have to measure that spectral line that we've got in the shop and estimate what its properties are going to be. I'm just going to put 0.5 millimeters in right here. So we've got 1 millimeter by 0.5 millimeters. That's going to give us a 0.5 millimeter cross section. And because this is all going to be loaded in tension, it doesn't matter if the shape's a little bit wrong because it's just going to be getting stretched. And I'm going to create that as a new component. I'm going to say OK. And that's going to pop up in there. And by default, it's going to have the properties of steel. Now, if you want to look up the material properties of spectra and compare them to the material properties of steel, go right ahead. Okay, I think this is close enough to being super rigid and super stiff so that it's going to work for us. Now, you recall that we turned off the truss section, so you can see our little eyeball there has a slash through it. Turn it back on, and now I have a nice super straight line coming right up there, right down there. This is going to be loaded in tension because everything's trying to rotate forward. And I've only got one in there. So now I'm going to do the same thing that I did with the truss sections. And I am going to move or copy. I am going to pick up, what's it called on here? Component 4, or you can just click on it right here. And I'm going to move it in, oh, just a minute. Remember to turn on create copy. I forgot that last time too. I always do. Move that over there. Take a look at it from the top. We don't want it to intersect right there. You see I came a little too far. That's moved 40 over. Let's just move that over minus 39, 38, 37. That looks pretty symmetrical to me. In fact, that's probably about as symmetrical as you can tie those knots. So if we're off by a little bit in our model, well, we're off by a little bit in real life too. Let's click OK right there. Now we have some truss members in there, some tensile truss members. And now what we have to do is we have to tell Fusion how these are jointed to the main structure. So what I'm going to do is I am going to come over here. I'm going to just change the name right here to component 4.1. Oh, this body right here. That should actually be a component. So when I did that move copy right here, I must have created as a body. So if you don't see two ropes showing up in here, just come in there and look for it under a body. You'll see that it highlights, and then we'll just go and we will tell it to create components from bodies. There we go. And now we should be able to come in here and we should be able to name this one rope 1 and name this one rope 2, or string, or spectra, or whatever you want to call it. And now if I click on this one, I'm holding down Shift right now. Skip the front and rear support because they're not connected. Oh, sorry, I should be holding down Control. So I've got those three parts selected, but not my supports. Okay, I've got truss section, rope, and rope 2. And now what I'm going to do is I'm going to construct those, assemble those, and these are going to be a rigid group. So that just locks everything together right in there. So nothing rotates or moves, and there we go. They are now locked. And that's all we need to do to add string. We draw the string, we create it. This now has the elastic modulus of steel and the tensile strength of steel, which isn't a perfect model for spectra, but you can create a spectra material just like we did for the custom hardboard material, and you can come in and you can hook that up. If you weren't 100% happy with your properties for the hardboard material, you can also come in here and for the truss section, you can come in here, go to your physical material. You can come in here, pick up your medium density fiberboard, and you can edit that, advanced, physical, and you can change some of these properties right in here. So maybe the density was a bit high, maybe the Young's modulus was a bit high. You could go back and you could change that again. That works even better if you've done some tests in the lab and you've got some data. Okay, great. So here's our structure all put together right in here. We're going to save that one more time. You'll notice that when you save it, each time you save it, it saves it as a new version. And this is really cool because what it lets you do is say you do something wrong, you can go back to one of your old versions that you've saved and you can revert to an older design. So just as you've got the design history right along here, you've also got various versions that you've saved. So in case you've completely forgotten what you've done, you can go back to where the state where you were 20 or 24 minutes ago. So it's never a bad idea to save right on there. All right, let's come over to simulation. Now it'll give you a few errors saying these are out of date because we've made changes to the structure. Not a problem. We can leave those up because that's still relevant to what the structure looks like without the cable, and we might want to do a comparison. So let's just take this study that we just did, and let's clone this study. And now we've got a new structural buckling study. And let's take our static stress study, and let's clone that study. And now we've got a couple new studies. Now I'm going to activate study 3, my new structural buckling that we haven't solved yet. This one's got the ropes involved. And I'm going to have to go through my contacts and do automatic contacts again because I added some new elements to this design. And then I've got this structure set up right in here. And let's just do that one more time. Let's just make sure that I've got all my contacts in there. Yep, it seems happy. So my structural buckling set up. I can do my pre-check. I've got all the information required. And then I can go ahead and I can hit solve. Tell it to solve one study. And while it's off solving that one, I'm going to come in here and activate study 4. Hit the little button right there. Do my contacts, automatic contacts. Absolutely magical that it does that for us. So it's going through and it's figuring out how that string interacts right up there. And let's go ahead and pre-check. Click here to select automatic contacts. 2 fully unconstrained groups in load case 1. Let's just do that automatic contacts again. Sometimes in this, we need to do an extra set of automatic contacts. And now it says that. I think that's because we've got 2 new structures that we added in here, each with multiple joints. So if you get that error message when you do a pre-check or tell it to solve, just go back and do that automatic contacts again. Now you should be able to go solve, and you should be able to say, solve one study. And now our results are out there. and you can watch them race each other as they go through Autodesk servers somewhere close to a generating station. It's pretty cool. Close. Now, while that's happening right on there, I just wanted to take a moment and say I talked about how finite element analysis takes a look at this structure by breaking things down into a mesh. We can come down here in the study that we're looking at, you can turn that mesh on. Now, this one, we're not going to be able to see it because the meshing is part of the cloud service. So let's come back to our previous study right in here that we've done, and let's activate that, and let's turn on the mesh. And now you can see what it's done is it's come in here and it's broken this structure down into tiny elements. And that you can see is on the smaller elements, on the smaller parts of our structure, they get smaller elements because they need more detailed analysis. And in here, okay, those elements tie together and it compares each of those elements to the others, hence the term finite element analysis. So I'm going to turn that off again, but if you want to see how it's doing its thing, that's how it's doing its thing. Okay, we're still waiting for some results right here, so I'm just going to center that, and in just a moment, one of these results should be available. I'm going to hit pause while I wait. There we go. Looks like we have some results here. So if I activate my latest study, and here we go. This was a structural buckling study. And as you can see, well, not too much has happened right on here, but you'll see that my buckling mode 1 is negative something, and it's showing me that the buckling has occurred because this is popped out right here. So again, negative buckling is when things go, when the force, instead of pulling down, pushes back up. So you've got to come into your different modes, and you've got to look for the first positive buckling failure. Now, hopefully, that will be greater than 1. And you can see that, oh, I've made it all the way up to -1, and that one's not buckling right on there. So this structure is going to hold up, but I just want to see what it's going to look like. That structure is going to need to be redone. I need more modes of failure because these modes of failure are all in the negative, and that's not what I'm looking for. Okay, so I'm going to just change my structural buckling study here. I'm going to right click on it, go into settings, and if you're getting something like that, and oh, don't move that around. Sorry, I saw that pop up on my other screen where I'm controlling the OBS Studio, and my mouse was over there, so I went and grabbed it, and it looks really realistic. So anyway, here we go. I want 100 modes of failure for this one. I should be able to just alter those properties in here. Study material, load case, structural buckling, study 2, settings, study 2, B we'll call it, and we'll change that to 100 modes of failure. Okay, that's study 2B, structural buckling right now. The results are all out of date. We're just going to go back and we're going to solve that again. Okay, so finish our results, get out of here, study 2B, go ahead and solve that because we needed more modes of failure in there. Okay, let's go, and while that's running, it had just solved our static stress. Let's take a look at our static stress results in here and see if that changed how our static stress is going to behave. And now you can see that because the load's coming up here, we've got a whole bunch more load happening in the tower. The tower is still pretty super stable though. You can see it's got dark colors indicating that we've got fairly high stress right in here. Our deformation may have dropped off, a little bit overall, But yeah, down here we've got a lot less red happening right back in here. So a lot less twisting and maneuvering going on right back in here. And so that looks like an overall better, stiffer structure with less material in the high safety factor zones. Now, one of the things that we can do is if we see sections like this that are all blue, they've got too much material in them. So we can shrink those down in our model and we can make them smaller and lighter. Even if something's green, we can make it smaller and lighter because these blue ones right here are somewhere between 6 and 8 times as strong as they need to be. If you want to know exactly how many times too strong they are, come up to inspect and you can create a surface probe and you can come in here and that one's 15 times stronger than it needs to be. And that one's 5 times stronger than it needs to be. Remember to try and look on both sides right there. Down here, this one's only 2 times stronger than it needs to be. That one's only 1.8. I probably wouldn't mess around with anything that was, getting down to 1.5. But if you're in the 2 or the 3 range, you could shrink that down. And definitely if you're in the 15 range, there's basically nothing happening in there, and you can probably shrink those members down quite a bit. Okay, so that's going to help you figure out where you can make this stronger and make this weaker. And let's see what's going on back here. Oh, it's telling us that our little string is going to break. I don't think that piece of steel is going to break. That's just the way we've got that modeled right in there. I'm not too worried about that at all. Okay, so we can cancel our surface probing, and there you can see the deformed structure. That one's going to hold up just fine, I think. And let's see, how's our job coming along over here? Simulation progress, I'm just waiting for that to fill out, so I am going to pause again. Okay, our results are back. And so now that was down here, our structural buckling study we wanted to take a look at. And now we've got 100 different modes of failure. So if we click in right here, we were at minus 0.9, minus 1 point, minus, aha, here's our first mode of buckling failure for this structure. It's predicting 1.5 times our load. It's predicting failure right in here again. Okay, but this time at 1.5 times load instead of what we had before, which was, I think, 1.4, I can't remember. Let's see, it's weird that it shows that side kicking out that far, but once buckling starts, weird things will happen. I see no positive failures before that, so you've got to look for that positive failure in there. And there you go, that one predicts that it'll probably be able to handle up to like 4.5 kilos. I didn't get a good practical reading on that one because I built my truss wrong and had this string interact with that node right there. So I can't tell you how accurate that is or not, but based on what I've seen, that's probably pretty accurate, aside from the fact that I think my elastic modulus for the hardboard is a little bit high. And again, we can figure that out by taking some actual measurements in class. So there we go. You can start in AutoCAD. Okay, we started with our AutoCAD drawing. We exported it as a DXF so that we got that shape into Fusion. And I'm going to come back to our design. Let's just go through those steps again. So we imported the drawing as a sketch. See how we just went back on the timeline right there? We extruded the drawing. We copied and moved the section. We applied some materials to it. We created a new sketch showing all the little holes that we could take across. We remembered to put a flat little bottom right out there so that we could apply the load to it easily. Then we came in here and we created a new sketch and extruded, oh, sorry. We extruded a rear support. Then we used a projection of a round hole to extrude the front support. We jointed those two supports in place so that they were attached to the structure. We created we created a construction plane. We created a profile for the rope. We added a rope. Then we copied the rope right across. And then we created a rigid group to hold the rope together in there entirely. And that creates a structure of our truss that we're then able to take over to our simulation environment. And in the simulation environment, we were able to set that up and so we could finish our results. In the simulation environment, we had to, we had already applied our materials. If the materials don't have the right values, you're not going to get the right results. We created load case. Our load case had one load right down here. Okay, we set that to 30 newtons, representing the 3 kilos of weight that we'll be applying. We put some structural constraints on it. Okay, so we had a fixed constraint at the back and a frictionless constraint at the front. We did a little bit of automatic contact generation so that everything would know where it was hooked together. And there you can see it created the contacts. We didn't have to really worry about that at all. And then we did a solve. If you're stuck in this right here and you can't get rid of the colors, that's because you need to finish your results. And now you can go back and you can set up and change your model. You can capture a screenshot of that, or there's something in here. You can come into your results and you can export your results as a web page, but a nice little screenshot of the colors of your truss and the deformation of your truss should show you the results. But most importantly, you can now sit down and with some degree of confidence, model your truss while you're sitting at home and save all the hassle of building it. You will still have to build a model and test it to make sure that you've got to validate your results. Okay, simulation is good, but it can provide bad results sometimes unless you test your model and are very sure that you know what's going on. So create a truss that you think is going to be good, that you think is going to be strong. Create a model, record what your model says it's going to fail at, record where it says the model is going to fail, and then come in and build and test that truss. This is really useful if you want to do a few different things. So for instance, I made this 40 millimeters apart in the middle right here. I'm going to go back to my design, okay? And where I did that copy right in here, there's that move command. If I double click on that, I moved that 43 millimeters already. I can come in here, I can move that another 20 millimeters out, and now I've got sitting 60 millimeters apart. You'll notice that because I used a surface to surface modeling, all my cross members remembered to move along with me. And now up here, when I moved those members apart, I can move that another 20 millimeters. Don't want to move 25. Must be zoomed out a little too much, or there we go. 10, 20. They're 20 millimeters wider apart right now. And now I can go back and I can do another simulation and I can say, am I stronger at a 60 millimeter gap or 40 millimeter gap? Or what happens if I move that up? Why does it want to do 25? Because I'm not zoomed in enough. I want to move it. Just cancel that. It's all messed up. What's going on there? Come in here and where was my move right here? Double click on that move. There we go. Now I'll be 80 millimeters wide and then come in and move my rope. So now I can come back and I can model this truss right here and I could say, well, how does my 40 compare to my 60 compare to my 80? Does one of them get stronger or does one of them get weaker as I move those truss parts further and further apart? And I could use that information to let me know what's going on. Now notice with the 80 that there is a little bit of a glitch right here. And so you'd have to come in here and where we did that extrude, double click on that extrude button in the timeline. There we go. And just make sure it's long enough now to go all the way through. Okay, and we just did that one. Oh, sorry, we just did that one. Double click on that one right there. Oh, I was clicking on the joint. Oh, that's because I was clicking on the joint. I wanted the extrude right there and pull that all the way through so that that's supporting right in there. Now you've got a nice new 80mm wide truss that you'll be able to test. So lots of things that you can do for testing your truss and finding a truss that you think is going to be strong and light. Now, one of the downsides of doing it with the AutoCAD import route is that you've got to go back and change your AutoCAD drawing, and then you've got to import again, and then you've got to come in and change all your designs in this model. Fusion 360 does have a way to create your design entirely parametrically so that it's fairly easy to change around, and I'll create a video showing you how to do that. That's an optional extra, but one that you might find really useful. Okay, right now, your assignment is to take this, take your design from AutoCAD, import it as a DXF, extrude, copy, extrude your members that come across, and run a simulation to see if your truss is going to stand. How long is that? What have I been talking at you for? An hour and a half now? I don't know why my YouTube channel doesn't have more viewers.